Hi everyone, my name is Gonzalo Mosquera and I am presenting our work Evaluation of Monte Carlo Dropout for Uncertainty Quantification in Multitask Deep Learning-Based Glioma Subtyping. Every year, approximately 100,000 people worldwide are diagnosed with diffuse glioma, which is a primary brain tumor. The diagnosis, prognosis, and treatment rely on tumor genotype and grade, which are currently based on tumor tissue analysis obtained after surgery or biopsy. Our aim is to move towards trustworthy AI-assisted glioma diagnosis using non-invasive imaging, consisting on various sequences of pre-surgical MRI, and we focus on quantification of model uncertainty. In our research group, a deep learning framework for glioma subtyping was previously developed. Preprocessed data goes through an encoder-decoder network to produce tumor segmentations. The output of the encoder and the decoder at each resolution level are used as features for a classification branch in order to perform the prediction of the IDH mutation status, the 1PNTQ codeletion status, and the tumor grade, leading to a multitask framework. Although the framework showed good initial results in terms of predictive performance, it was lacking uncertainty quantification, which is a paramount component of trustworthy AI, especially in medical applications. The objective of this work was to integrate uncertainty quantification into a multitask deep learning framework for glioma subtyping. We adopted Monte Carlo Dropout as the uncertainty quantification method, as it remains one of the most widely applied approaches for approximating Bayesian inference in deep learning. And we performed a systematic evaluation of Monte Carlo Dropout by evaluating its parameters, with the aim to assess its overall value for building trustworthy AI systems in our medical application. We train the model with the chosen dropout rate, and most importantly, we keep dropout active during inference. As a result, each forward pass gives a slightly different outcome. For example, the first pass yields a first prediction, and then the second pass gives a second prediction, and the third pass a third prediction, and so on until we collect m predictions. Together, these predictions form a distribution rather than a single output, which we then use to quantify both epistemic uncertainty and aleatoric uncertainty. For the segmentation branch of our framework, we generate voxel-wise uncertainty maps for each patient. From these maps, we derive case-level uncertainty scores using two strategies. First, averaging over the brain region, and second, averaging over the predicted tumor region obtained from the Monte Carlo Dropout ensemble. For the classification tasks, we directly compute case-level uncertainty scores, allowing us to compute the predictive uncertainty across all tasks and disentangle its epistemic and aleatoric components. We conducted experiments varying the dropout rate from 0.2 to 0.6 in increments of 0.05, and the number of Monte Carlo samples from 10 to 100 in steps of 10. The framework was evaluated in terms of both calibration and predictive power. For calibration, we use the expected calibration error and negative log likelihood for classification, and the Pearson correlation between uncertainty scores and dice scores for segmentation. For performance, we employed AUC-ROC for classification and dice score for segmentation. The findings of our work can be summarized in the following points. First, uncertainty estimates stabilize at 20 to 30 Monte Carlo samples. In the classification task, aleatoric uncertainty was higher than the epistemic component, and the opposite was observed in the segmentation task. Moderate dropout rates led to better performing and more confident models. The optimal model was a Monte Carlo ensemble with dropout of 0.25 and 30 samples. When computing a case-level uncertainty score, a task-specific strategy, namely averaging in the tumor region, led to higher calibration. Uncertainty calibration analysis should be paired with model predictive power for a comprehensive model assessment. And when properly tuned, Monte Carlo Dropout yielded good performing and well-calibrated models for our medical application, thus enhancing model trustworthiness. Thanks for watching, and if you are interested in knowing more about our work, please refer to our paper or visit our poster at the Unsure workshop on September 27th.